We started by looking at how to make feedback amplifiers, to be precise, how to take the difference between the input and feedback quantity. Now, you can do it with any device because it senses the difference between voltages at two terminals. So, you can use that to take the difference, but if you take a single transistor and try to apply one of the voltages here and other one here, this will work, and there are circuits which use this, but the only issue is for it to be a universal block, for it to be an easy to use block, you would not like to have bias currents flowing into this, and also you don't want very low impedance inputs. You would like high impedance inputs so that you can sense without affecting what you are sensing. Okay. So that some kind of heuristic reasoning gave us this. So we do have already a transistor amplifier which amplifies the difference between V1 and V2. The only disadvantage of this is that V2 sees a very low impedance input. So to drive the very low impedance input, we will use a buffer. The input of the buffer is assumed to have high impedance. So that again V2 also sees a high impedance input. So this should work for us. Now the only voltage buffer that we know of is the common drain amplifier. So we are going to use that. Okay. So this is the circuit that we finally get, and what we expect from this is that the current in the MOS transistor and the load will be proportional to V1 minus V2. So we have derived the topology, now we still have to do the analysis to see that it works. Okay. I will rearrange this. Again, this is a familiar circuit, but I thought I will provide some reasoning behind why people might have come up with this. So it's quite important, not only in analog circuit design, but in anything else, to link something that you see as new thing to whatever you know, right? That's the only way you will remember. If you see a number of isolated facts, you will not going to be able to remember it. If you know a number of basic things, and any new thing that you see can be described in terms of the basic stuff. So if you know the logical linkage between the two, you will be able to remember it easily. Okay. I will redraw this as it is normally drawn. So this is the circuit we have. Now, if you draw it this way, the symmetry between V1 and V2 is very clear as far as the MOS transistors are concerned. Okay. So once you have this, then the natural thing is, it looks very much the same. So then can I put a load resistance here also? Okay. Because it looks exactly the same. So we don't know what may happen. We will make it fully symmetric. That's one of the possibilities. We don't have to do it, but that's one thing that could potentially be done. Okay. So the part below this is fully symmetric with respect to V1 and V2. Okay. So on the top side, we can have load on only one side like we started off with, or we can put load on both sides. Okay. So now that we have got the circuit, we have to analyze it and see if it works the way we expect it works. Okay. So one of the things that we want from a block like this, okay, this is just a block diagram, and this gives me V1 minus V2. Now, when you make a circuit implementation of this, V1 is some voltage with respect to ground, okay, and V2 is another voltage with respect to ground, and we have certain output voltage or current. Let's for instance take the output voltage, and we want this to depend on V1 minus V2. Okay, the block diagram, the way it is drawn, by definition it gives you V1 minus V2, but a circuit does not have to do that, right? So the output can be some function of V1 and V2, but not necessarily as a difference, right? What I mean is Vout could be A1 V1 plus A2 V2, where A2 is not minus A1. Okay. In this case, you certainly cannot say that the output depends only on the difference voltages. So the thing we want for to subtract the feedback quantity from the input quantity is that it should give you only the difference. Okay. So we would like something like this, but in general you will get something of this sort. Is that okay? So because this is the quantity of interest, V1 minus V2, what we can do is we can try and express everything in terms of V1 minus V2. Now that alone won't be sufficient because you can't always do this. For instance, let's take this case where Vout is A1 V1 plus A2 V2. This I can rewrite as in terms of V1 minus V2. Okay. What will be the coefficient of this? I can't do just this one. I also need V1 plus V2. Right. What will be the coefficients here and here? In this case, it's plus A2, so is this correct? A1 V1 plus, yeah. Okay. So if A2 is exactly minus A1, this part will vanish. The output responds only to the difference between the inputs. So ideally that's what we want. That's why we put it in this form. In general it will be like this, right? It will be some function of V1 and V2. If it is a linear function, it can be written like this. If it's a nonlinear function, it can be like this. But what we want is predominantly V1 minus V2. Okay? Because we know reality, it's not going to be only responsive to V1 minus V2. We write it in this form. Okay? This is just the convention. You can write it here, you can write it like this here, or you can write it like this. The two are exactly the same, but the second one brings out the more significant aspects for us. Okay, we want to amplify the difference, so it explicitly shows you the difference, but it also shows you that it amplifies the sum as well, which in general is an undesirable quantity for us. Okay. So this is sort of some preliminary to analysis, because we can go and analyze the differential pair with V1 and V2. But it's far more convenient and useful if we analyze it in terms of V1 minus V2 and V1 plus V2. So to summarize, if you have any circuit with two inputs, V1 and V2, and let's say an output voltage Vout, it could also be a current output. The output will be some linear function of the input voltages, or if it's a nonlinear circuit, it could be some function of V1 and V2. Okay. But since we want the difference between V1 and V2 to contribute predominantly to the output, we rewrite this as A1 minus A2 by 2 okay. And if it's a nonlinear circuit, you really cannot separate it like this, okay, in general. You can't do this because you will have all higher order terms also involving V1 and V2. But again, we would like f of V1 minus V2. If this is of this form, that's the best thing, okay. But it's not always of that form. So again, I think you can write it as f of the difference voltage and the sum, okay. So this V1 minus V2 is known as the difference input, okay, or the differential input. And this is known as the differential gain. And in general, A1 and A2 could also be frequency dependent. That is, it could be A1 of S and A2 of S. Okay. And this is the second part is normally split as V1 plus V2 by 2. Okay. V1 plus V2 by 2 is nothing but the average of the two voltages. So this is known as the common mode input, and this is the common mode gain. Okay. We have two input voltages V1 and V2. They can equivalently be represented by two different inputs which are dependent on V1 and V2. We can take the difference, that's the differential input, and we can take the average, that's the common mode input. So we can also express the output in terms of the differential and common mode inputs. And if we are interested in a block like this, right, where we want to subtract V2 from V1, then we would want the differential gain to be non-zero and the common mode gain to be 0. Okay. So this is just a matter of definition, and we will use this in the rest of the analysis. Okay. But what I want you to understand is there is nothing special going on here. We have just redefined the variables to be differential and common mode. That's all. Because we want the differential output, it brings out what we want more easily. So given inputs V1 and V2, we can define V difference to be V1 minus V2, and this is the common mode or the average voltage to be V1 plus V2 by 2. Okay. Now we can rewrite V1 and V2 in terms of these two quantities. V1 is the common mode voltage plus the differential voltage by 2. Okay. And V2 is the common mode voltage minus the differential voltage by 2. Essentially, you think of the two voltages as some increment above the common mode and some increment below the common mode. Okay. So this can be now be written as VCM plus VD by 2 and VCM minus VD by 2. Okay. This RL we already had because we thought of M1 as the common source amplifier, which got us the difference between V1 and V2. The other one we put just to complete the symmetry of the circuit. Okay. So now we can go ahead and do the analysis in terms of the common mode voltage and the differential voltage. Okay. So what will happen if VD is very large? How do you think the circuit will behave? Like what will happen to the output voltages VO1 and VO2? What will be VO1 and VO2 when the differential input is 0? Same. And what is that equal to? So because of the symmetry in the circuit, you can use symmetry for analysis without writing equations, right? So if you have the same voltage as VCM and VCM here, and the gate voltages are the same and the source voltages are the same. So you expect the current to divide equally between these two, and each of the output voltages will be VDD minus I0 RL by 2. Okay. As you increase VD, the source voltage is the same. The gate on the left side will go above the gate on the right side. So more current will flow through the left transistor. That will happen until all of the current flows through M1. Okay. Similarly, if VD becomes negative, more current will flow through the right hand side transistor, and you go on increasing VD, at some point all of the current will flow through that transistor and it will stop there. Okay. That's the type of characteristics you expect. And it will be symmetrical for positive and negative VD. That's also something you expect just from looking at the circuit, right? If I raise the left side or the right side, the effect you will see will be the same, except for an interchange of the left side and the right side. So now we can so first let's just do the lab signal analysis of the differential pair. Let's assume that VCM and VD both are DC voltages or slow varying voltages, so that we don't have to take into account the parasitic capacitances. And let's also use an idealized model of the transistor in which there is no channel length modulation. Okay, and both of them obey square law exactly. So the bottom current source will also be implemented with a transistor, but for now I will use an ideal current source. Okay. Let me call this I1, I2. So, and maybe this voltage is Vx. Okay. So we know that the sum of these two currents, I1 and I2, is I0. Okay. So we just write the equations. This is one of the currents plus this whole thing equals I0. Okay. And this can be simplified to, this is the sum of squares. So Is okay? So what I am doing here is to just try and find the value of Vx. Okay. Yeah. So this gives me this. From this I can calculate the value of Vx. That also has some interesting properties that we'll see afterwards. But my primary interest now is in finding V out. Okay. Let me, just like every other voltage, the input voltage we decomposed as common mode voltage and a differential voltage. We can do the same for the output voltage. In this case, we define two output voltages. I mean, note that I can define each of these, let's say VO2 and VO1 separately as output voltages, or I can take the difference between the two, right? So maybe I'll define it separately in the beginning, and after that I'll take the difference. So what is VO1? What is the value of VO1? It's VDD minus I1 R1, that's all. Similarly, VO2 is VDD minus I2 R2. So from this we'll be able to figure out what that is. Okay. And we already have the expression for this whole thing. Okay. Similarly, the other one will come out to be some complicated expression like that. So let's, yeah, so this is fine, and VO2 will be RL, sorry. There is a square inside this also. Okay. So it's some complicated expression. We'll see the graph of how it behaves afterwards. Okay. Now, what is the small signal gain? Small signal differential gain, that is the increment in VO1 because of an increment in VD. How much is that? Which is the linear term in this one? Huh? VD by 2. So that the whole thing will give you what? So this is not the derivative. The linear term will be, if I ignore everything else, what will I get? Into 2 times VD by 2 times this whole thing. Okay. And again, I can ignore this square term in the whole analysis. All I did was I expand this. I get the square of the first term, the square of the second term, and the linear term. So I have taken only the linear term there. And what is that? Sorry. Okay. And what is this thing? What is the term in the middle? It is, if you look at it, each transistor carries a current I0 by 2 in the quiescent condition. Okay. So if you have a current I0 by 2, the GM will be square root of 2 times the current, which is I0 by 2 times mu Cox, the aspect ratio. So this term is nothing but the GM in the quiescent condition. Of course, we can reduce the whole thing to small signals and get it, but once in a while it's okay to do this just to see that the analysis is correct. Okay. The small signal gain happens to be similar to what it was before, right? Before, if you had a common source amplifier, you would have got a small signal gain of GM times RL. Now we have got half times GM times RL. So that is a difference that we have to explain, but it has the same form as before. Okay. So in large signal, of course, it is some nonlinear expression that we already know, because as you go on increasing VD on one side, ultimately the current flows entirely to one side, and after that the voltages at the output don't change at all, right? Once all of the current switches to one side, you will have VDD here, VDD minus I0 RL here and VDD here, and things don't change anymore. So that already says that the whole circuit is nonlinear, which is nothing unexpected. But if you look at the small signal gain around the operating point, it is similar to that of a common source amplifier. Okay. And what will be the other one? It will be just plus, because only the sign of VD is different in the first order term between the two expressions. So by making the circuit symmetrical, by adding another load, we have two outputs, and the gain from the differential input to the two outputs are equal and opposite. Okay. Not many new things here, because I think you're at least familiar to some extent with differential circuits, but this is what happens, that the gain from VD to VO1 is something from here to here, and gain from VD to VO2 has the same magnitude but the opposite sign. Okay. So what does this say? VO1 and VO2 also swing equally and oppositely from the common mode voltage. Okay. If you apply a certain VD. Is that okay? So in a fully differential circuit, by fully differential I mean the circuit must be fully symmetrical, something like this. The input really consists of two inputs which are applied symmetrically to the circuit, and the output consists of two outputs which are taken out symmetrically from the circuit. In that case, if you look at the outputs, they will also vary symmetrically around a common mode voltage. Okay. We will make this more concrete and we will make what are known as common mode and differential equivalent circuits, which will considerably ease the analysis. But one thing I have to say is all those things are true only when the circuit is fully symmetrical. Okay. Now, one of the interesting things is this, what will be Vx? What will be the, what do you guess is the small signal gain from Vd to Vx? What is the small signal gain from Vd to Vx? What should it be? Vd, yeah, from Vd to Vx. 0. Why? Yeah, I mean, even logically speaking, it is 0, right? It can't be anything else. Because, first of all, it should behave the same way from this input as it does from this input. Okay? So, that itself tells you that it has to be 0. Because when you are increasing this side, you are decreasing the other side. Okay? So, it has to have the same gain for this positive increment on that side and negative increment on the other side. So, that logically, for a fully symmetric circuit, because of symmetry, it has to be 0. Okay. So, this whole thing is known as the line of symmetry, right. So, because you raise things on one side and reduce things on the other side, or make the thing voltage fall on the other side, and because of the symmetry of the circuit, however, I mean, in whichever way the left side voltage affects this point, the right side also should affect it in the same way. And the only consistent solution is a 0 gain. Okay. Even without the details of circuit, you can figure it out. It's for any circuit. Again, the circuit has to be fully symmetrical. Okay. Now we can evaluate the, so does it mean that Vx doesn't change at all? Only for small signals. What happens for large signals? Huh? No, forget VCM. Let's, we are only analyzing the change with Vd. Okay. VCM is a constant. So what will happen with Vd? He said that only for small signals it will remain at 0, meaning for small increments in Vd it doesn't change. What happens for large increments in Vd? So one thing is, clearly, let's take the extreme case where all of the current is flowing in one side. Okay. So no current is flowing here, so this is as well as an open circuit. So from this input to this output, it's a source follower. Okay. So it will follow Vd by 2. That's what we expect. Okay. And that's actually apparent from this expression also. So I can write Vx as okay. First of all, it's an even function of Vd. Okay. That again says that the slope at the origin is 0. When Vd equal to 0, it is 0. If it's an even function, it will not have a first order term in the Taylor expansion. So it has to be 0. Okay. And what is this quantity, excluding the last term? What is this? What is that thing? What is that quantity? It is the overdrive of each MOSFET in the quiescent condition. Okay. Again, you get I0 instead of 2 I0 because only I0 by 2 is flowing through each MOSFET. Isn't it? If a current I is flowing through a MOSFET, its overdrive is mu Cox W while this whole thing. So now I is I0 by 2. So clearly when Vd is 0, you should get Vcm minus Vt minus the overdrive. Okay. So we have Vcm here in the quiescent condition and Vcm minus Vgs is the tail node. By the way, this node is known as the source coupled node or the tail node of the differential pair. Okay. So that is nothing but Vcm minus Vgs, which is Vcm minus Vt minus the overdrive. So that's what we have. But in presence of Vd, we will have an additional term minus Vd square by 2. Okay. So if I plot Vx versus Vd, and in this whole analysis Vcm is assumed to be a constant, obviously. When Vd equals 0, I get Vcm minus Vt minus the overdrive, and it will be some even function. So that is obvious from the appearance of only Vd square in the expression for Vx. What happens when the argument inside the square root becomes negative? I mean, for large enough Vd it will happen, right? What does it mean? Huh? No, I mean, if the argument inside the square root is negative, we get an imaginary answer. What does it mean? Huh? No. Not necessarily. Diode region depends on the drain voltage. Now, we have not even looked at the drain voltage. What does it mean? One of the MOSFETs is cut off. So basically this rather the sum of these two currents is I0. That is always true. But the expression for the currents is valid only when they are on, right? Not when they are off. So when the current is steered fully to one side, you can't use this expression to get the current of the MOSFET. So it's just that it has gone beyond the range of validity of the equation. Okay. And what is the limit? What is the point at which all of the current goes through one side? What is the value of Vd? How do you calculate that? Yeah, one thing is you can equate the term inside the square root to be 0, but it's better to calculate it from the circuit itself. Okay, because you are not sure that that is the point at which it goes out of validity. It could be before also, right? So when all of the current is flowing through one of the MOSFETs, or it just started flowing through one of the MOSFETs, the current through here is I0 and the current through this is just become 0. Okay. So what is the voltage across this device? So it is just turned off. Okay. All of the current has just steered to one side. So this voltage goes on decreasing and it becomes equal to Vt. And this becomes equal to what? So, I was not sure if that was clear. When Vd is 0, I0 by 2 flows here and I0 by 2 flows here. As I go on increasing the value of Vd, this current increases and this current decreases. Okay. When the current on the right side just reaches 0, okay, the voltage across the gate source of the transistor is the threshold voltage. Okay. And this side it will be, the current is I0, so it will be Vt plus the overdrive corresponding to I0. So the difference between the input voltages is Vd, which is also equal to the difference between the gate source voltages. Okay. So for Vd equals 2I0 by mu Cox W by L, all of the current flows through M1, where M1 is the transistor on the left side. Okay. And for voltages more negative than minus square root 2I0 by mu Cox W by L, all of the current flows through M2. Okay. So let me call this Vd max. So up to plus minus Vd max, it will follow this. Follow the equation that I wrote here. What happens beyond that? What, with what slope? Saturate. So the question is, this is the expression for Vx versus Vd. I mean, every expression that we have evaluated so far is valid only in this region, between minus Vd max and plus Vd max, because we sum the two currents to be equal to I0 and then we use the square law to get each of the currents. So this is the range of validity of those expressions. In Vx versus Vd, what happens beyond this? So one of the answers was that it goes linearly, the other answer was that it saturates. Saturates. What happens? Goes up linearly and it saturates. Why? I mean, everything saturates in reality, but besides that, it goes up linearly, right? Because when all of the current is flowing through the left side, I have this circuit. I go on increasing Vd, this will go on increasing. And what is the slope of this voltage versus Vd? Half, because what is applied is Vd by 2, okay? This follows Vd by 2, so it will be half. And similarly on the other side, it does this. So it is an even function, even then. Only thing is the expression that we evaluated before is not valid. This different expression is valid. The slope here is minus half and the slope here is half. Okay. This is how Vx behaves with increasing Vd. We also need to look at how the output voltages behave with increasing Vd. We have already qualitatively evaluated it, but we can look at it quantitatively also. But before going to that, have you seen some characteristics like this? Is this characteristic useful for anything? What's that? Yeah, so it's an even function, so y equals mod x will be something like this. So it is close to that. So where do you use such a circuit? Y equals mod x? Rectifier. That's what it is, right? So if you have a rectifier, if you have a sine wave, it will give you something like this. Okay. So you can use this as a rectifier in CMOS without using diodes. Okay. Only thing is, if you have very small voltages, the slope is 0. You will not see any change at all. For large voltages, it behaves like a rectifier. Okay. In general, even functions are useful to detect the strength of signals. If you think about it like, if you think of the definition of RMS signal, it has something to do with the square of the signal, right? So in general, the square or the even function is involved when you want to detect the strength of the signal. Okay. A lot of times we deal with signals, in fact most of the time I would say, whose average value is 0. So if you just make linear operations on it, you will not get the strength of the signal. You will have to do something nonlinear to obtain the strength. So one of the things you can do is to rectify it. Okay. So in general, even order nonlinearities give you a measure of the strength of the signal. It may not always be RMS value or anything like that, but it will give you an idea of what strength it is. Okay. So this can be used for a rectifier, but this was actually some sort of side business. Our main interest was in VO1 and VO2. We happen to calculate Vx, and then we also find that it is interesting and useful in some applications. So if you do want to make a rectifier, by the way, this is a rectifier for the differential input Vd, right? We have not yet seen what happens for the common mode input. So if you have VCM plus Vd by 2 and VCM minus Vd by 2, and you look at this as the output, this gives you a rectified version of Vd. Okay. So the next thing is to calculate VO1 and VO2. Equivalently, we can also calculate the individual drain currents, I1 and I2, and plot them against Vd. Okay. What are I1 and I2 for Vd equal to 0? I0 by 2. Both of them are equal and equal to I0 by 2. And what we already know that beyond this range, plus minus Vd max. So let's say this is plus 2 I0 by mu Cox W by L. What happens to I1? I1 is the current through the left side transistor. I1 becomes equal to I0. Okay. And I2 becomes equal to 0. Similarly, beyond the negative of that quantity, I have this, and of course they have to cross in some way in the middle, so they probably do something like this, and they will be symmetric. Okay, I1 and I2 will be just flipped versions of each other. That's because of the symmetry in the circuit. Okay. What will be the slope at the origin? And not at the origin, when Vd equal to 0. What will be the slope? What is the slope of I1 versus Vd at Vd equal to 0? Yeah, it's we have calculated it here. This is I1, right? This is I1 and this is RL. So, and this whole thing was, the slope of that was nothing but Gm by 2. Okay. Isn't it? This VO1 is VDD minus I1 RL. Okay. So the slope of V01 is slope of I1 times RL, okay, or rather minus of that. So this whole thing is Gm by 2. Think about it, it should come out to be Gm by 2. So again, the current in a differential pair behaves very much similar to the current in a common source amplifier. Okay, in a common source amplifier, the slope of the drain current with respect to VGS is Gm. Here it is Gm by 2. I still have to explain why there is a factor of half, but it behaves similarly, and the voltages also behave similarly. But if we complete the symmetry of the circuit, we see that all currents vary symmetrically. And one other interesting thing is that we have the tail node Vx, whose voltage varies as an even function with the input difference voltage. Okay, that is useful in some applications. So we will do this in more detail in a more systematic way, but I think the summary is pretty clear. I started with the large signal analysis because we normally do small signal analysis. I thought for a change we will do large signal and then go to small signal. So to summarize, we got the differential pair by buffering a common source amplifier, by buffering one of the inputs of the common source amplifier. It's called a differential pair because it happens to respond mainly to the difference between the input signals. We have not seen that yet, but we will see that soon. Okay. And we completed the symmetry. So here all the comments I am making are about the symmetrical circuit. Okay. So here the output voltages I mean the increment in output voltages. Okay. And this node it's known as the tail node or the source coupled node. So this circuit is also called the source coupled pair because we took one transistor and coupled it to we took a source follower and coupled it to the source of the common source amplifier. Okay. So this is known as the differential pair of the source coupled pair. We also saw that the tail node voltage Vx is an even function. An even function by definition means that small signal gain is 0. Okay. And it can be used as a rectifier. So the bottom line is we have some circuit that behaves, that takes the difference between the two and gives you some output proportional to the difference. Okay. And the constant of proportionality is similar to that of a common source amplifier. Why is there a factor of 2 difference? So what happens is that, so I erase that. We use the voltage buffer to couple to the source of the common source amplifier. If the voltage buffer was ideal, okay, that is it had 0 output resistance, then all of the input difference would appear across the common source amplifier and you would get Gm as the proportionality constant between the input difference voltage and the current in the transistor. Now the source follower itself has a finite output resistance, non-zero output resistance. So because of that, it turns out only half the voltage appears across each of the transistors. Okay, that's why you get half as this. See, the gain from here to here is GMRL, right? So if I do have an ideal voltage buffer, with R out equals 0, then whatever I apply here also appears here. Okay? But what is the impedance looking this way? 1 by Gm. What is the impedance looking in this way when you use a real source follower? Also 1 by Gm. Okay? So we have used a buffer, but it's not an overwhelming buffer. I mean, its output resistance is not much lower than that of the load. In fact, it's exactly equal. So there is a voltage division of half. Only half the voltage, if you apply V, only half the voltage appears here. So that gives you a proportionality constant of from this voltage to the output current, it is still Gm. But from the actual input voltage to this current, it is Gm by 2. Okay? That's all. We will see this in various different ways. Any questions?